In this video, we're going to discuss divisibility. So the definition of modular arithmetic tells us that if a and b are integers and m is a positive integer, then a is congruent to b mod m if and only if m divides a minus b. So before we actually look at this definition and actually do some practice with it, I want to make sure we're very clear on the concept of modular arithmetic or mod m. So let's look at just mod 4 since that's what our first example will deal with. And mod 4, remember when we're talking about mods, we're talking about remainders. We're very interested in what the remainder is. So if I take something and I divide it by 4, I could possibly get a remainder of 0, or I could get a remainder of 1. I could get a remainder of 2, or I could get a remainder of 3. Now if I got a remainder of 4, that would really be the same thing as a remainder of 0, because 4 would be divisible by 4 exactly, which means a remainder of 0. So these are really my only options, because we always like to look at the smallest values. So now if I'm looking at mod 4 and looking at my number line I've drawn, this would be 0, 1, 2, 3, just as we normally would think so on a number line. But with mod 4, the value of 4 divided by 4, is a nice even number that has a remainder of 0. And 5 divided by 4 has a remainder of 1. And 6 divided by 4 has a remainder of 2. And similarly, we could go in the opposite direction, where negative 1 would actually be negative 4 divided by 4 with a remainder of 3, and then 2, and then 1, and then 0, etc. So we can see what the pattern is basically just 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, etc. So what we're looking for in our first example asks us, is 2 congruent to 6 in the world of mod 4? So looking at mod 4, 2 and 6, if you'll notice, both are 2, which means if I take 2 divided by 4 or 6 divided by 4, my remainder is 2, exactly the same. So that's good. So that means yes, they are equivalent. Now what I want to do instead is look at my definition. And my definition says I can determine that without making a number line and counting everything out by saying, is the difference between these two values divisible by 4? And that is what we're asking here. So we're saying, does 4 divide 2 minus 6, or 6 minus 2 would give us the same result. So does 4 divide negative 4? And 4 does divide negative 4, and therefore we know that yes, 2 is congruent to 6. So we're not saying that 2 is divisible by 4, or that 6 is divisible by 4, but that these two are equivalent because the differences in their remainders is divisible by 4. So let's look at our next one. 24, is 24 congruent to 14 mod 6? So again, we're asking, does 6 divide 24 minus 14? Does 6 divide 10? And in this case, 6 does not divide 10 evenly, and therefore, no, these are not equivalent. Again, we could draw out a number line and we could see that visually, but hopefully you get the basic idea of modular arithmetic. We've just looked at the definition of modular arithmetic, and I want to look at a theorem that really follows from that. And I feel like this theorem is pretty straightforward. Essentially, it's saying all the same things we had before. A being integers, m is a positive integer, then a is congruent to b mod m if and only if, and then a mod m is equal to b mod m. So really all we're saying is if the remainders are equal to one another, then they are congruent. And that's what we talked about when we looked at our last slide. But let's kind of look at it in terms of the mathematics. So I put the same two examples that we had on the last slide, and I just want to look at it in terms of when we looked at the division algorithm. So if I'm looking at 2, I'm saying, does 4 divide 2? And again, we know the way that we can write this. We're saying 4 times some number plus some number equals 2. That's what we want to look for. So in this case, 4 times 0 plus 2 does equal 2. And then if I were going to write that in terms of r, which is the remainder is equal to 2 mod 4. So 2 mod 4. So notice what I'm building up to here. A mod m, I'm saying 2 is equal to 2 mod 4. Let's look at 6. So does 2 divide 6? Sorry. Let me try that again. Does 4 divide 6? I got confused for a minute. And so again, the way that we would write that is 4 times some number plus some number, using the definition of division. And in this case, we would say 4 times 1 is 4, plus 2 is 6. And again, the remainder of 2 would be equal to 6 mod 4. And so notice what I've just shown you is that, yes, in fact, we already knew these were equivalent, but now I'm just showing you in another way that 2 is equal to 2 mod 4, 2 is equal to 6 mod 4, and therefore 2 mod 4 is equal to 6 mod 4, and therefore we can say, yes, this is true. Let's look at our other example, and again, we previously showed that this was not congruent, so let's take a look at how we might show that mathematically. So we're saying, does 6 divide 24? And if we take 6 divided by 24, we're saying 6 times some number plus some number is equal to 24. In this case, 6 times 4 is 24 plus 0. So how would I write that? I would say that my remainder of 0 is equal to 24 mod 6. And now let's look at the other one. We have 14. So does 6 divide 14? And again, we're saying 6 times some number plus some other number. This one would be 6 times 2 is 12, plus 2 is 14. And notice here, my remainder is 2. So 2 equals 14 mod 6. And obviously, these values are not equal. Therefore, 24 mod 6 does not equal 14 mod 6. And therefore, we can say, again, that 24 is not congruent to 14 mod 6. Now that we have a basic framework for modular arithmetic, I want to look at a few theorems and their proofs before we do any actual computation. So the first theorem says the integers a and b are congruent modulo m, which is just a is congruent to b mod m. And then we have this if and only if word, and keep in mind whenever we have if and only if, that means you have to prove it in both directions. So assume this, prove this, and then vice versa. And what am I trying to prove? There is an integer k such that a is equal to b plus km. So notice here I'm going from congruence to an equation. So let's start by assuming a is congruent to b mod m. So I'm assuming, we'll call this p, proving q. So let a be congruent to b mod m. What do I know about when things are congruent? Well, based on what we've learned in this video, then we can say that m divides a minus b. Why can I say that? By the definition of congruence. Now, if m divides a minus b, then I can say that a minus b is equal to km for some integer k. And again, how do I know that? By definition of divisibility. Now think about where I'm trying to get to. A is equal to b plus km. I'm really close here. By addition, or you can even be specific by addition of b, because I'm going to add b to each side, then A is equal to b plus km. So I've shown that if P is Q, then Q must be true. Now I have to show if Q, then P. So assume A is equal to B plus Km. Then A minus B is equal to Km by subtraction. And as you can see, I'm just kind of going in the reverse order. But what I have to show then is that this is true. So if A minus B is equal to Km by subtraction, what does that tell me? That tells me that M divides A minus B, so A is congruent to B mod M. And again, I didn't give the reasons for each step there just because I'm using the same reasons as I did in the proof above. So I've proved this one in both directions. Let's take a look at another theorem now, and we're actually going to use the last theorem that we proved to help us prove this. So this theorem says, let m be some positive integer. If a is congruent to b mod m, and c is congruent to d mod m, then a plus c is congruent to b plus d mod m, and a times c is congruent to b times d mod m. So again, this is not an if and only if statement. That's just an if then, so it's just a one direction proof. But there's two parts. I have to prove that this is true, and I have to prove that this is true. So before I prove either of those things, let's give ourselves some assumptions. We're going to assume, and again, if I wrote this as a proposition, it would be if blah, 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 then, and so I'm assuming the if part. So assume A is congruent to B mod M. Then, what does it mean to be congruent? Then I can say that A is equal to B plus Km for some integer K. Assume also C is congruent to D mod M. Then C is equal to D plus Lm for some L that is an integer. So I'm just going to use those as assumptions for each of the two parts of the proof that I'm going to go about proving or showing. So I'm going to start with A plus C. By substitution, instead of A, I'm going to plug in B plus Km. And instead of C, I'm going to plug in D plus Lm. From here, I'm going to just do some rearranging. I'm going to use both the associative and commutative properties, and I'm not going to write down each step. I'm just telling you the steps as I go. I'm going to use both the commutative and associative properties to rewrite this as B plus D plus Km plus Lm. And then by the distributive property, I'm going to call that B plus D equals B plus D plus M times K plus L. Now, what am I trying to prove? I'm trying to prove that these things are congruent modulo M, which means
right now I have A plus C is equal to B plus D plus M K plus L. So A plus C minus B plus D is equal to M times K plus L. And what does this mean? If we have M times K plus L, so M divides A plus C minus B plus D. So A plus C is congruent to B plus D mod M. So a lot like that last proof that we did, I need to show that M divides it and therefore that they are congruent. So I'm just using a lot of definitions. I apologize I didn't write down the reasoning for each of those steps, but I feel confident that you can look at our last example and write down those yourself. I'm just dealing with limited space here. So now let's do the exact same thing. I have AC. A times C is congruent to B times D mod M, so I have to take A times C. And A times C would be, by substitution, B plus KM times D plus LM. And again, I can do some math, some distributive properties. So I have BD plus BLM, not D, BLM plus KDM plus KLM, that's horrible handwriting, KLM squared. And really, I'm just trying to write this kind of in the same way that I did the last one. So can I do that is the question. Well, I can say that this is BD plus M times VL plus KD plus KLM. So what does that tell me? So A times C minus B times D is equal to M times all of that, BL plus KD plus KLM. And again, if I can do that subtraction, and that subtraction results in M times something, then M divides all of that. So M divides AC minus BD. So AC is congruent to BD mod M. Let's take a look now at those same theorems again and actually use them in an example. Before we actually use those theorems, though, I want to look at just some regular modular arithmetic with you. So this one says, let's find 7 plus 11 mod 5. If I were to find 7 plus 11 mod 5, then really what I'm going to do is take 7 plus 11 to get 18, and then say 18 is congruent to, so it's not equal to, but it's congruent to, and then I'm going to think about if I took 5 into 18, what's my remainder? And the remainder would be 3, because it goes into 15 evenly with 3 left over, so 3 mod 5. So again, notice I switched from equals to congruent to. Now let's take a look at the theorem. The theorem says if A is congruent to B mod M, so essentially they're saying, let's take a look at 7. What is 7 congruent to mod 5? Well, if I took 5 into 7, that would be a remainder of 2, so 2 mod 5. And 11 would be congruent to 1 mod 5. So if I wanted to do this question again, 7 plus 11 would be congruent to 2 plus 1 mod 5. which would be equal to 3 mod 5. Now let's take a look at our other practice. We have 7 times 11. So again, without our theorem, 7 times 11 would be 77, which would be congruent to 2 mod 5. Again, using what we learned here, we could also say that 7 times 11 is congruent to 2 times 1, which is equal to 2 mod 5. So again, not a proof. We've already done the proof. This is just showing how those theorems might be used in an actual example. I also want to point out to you some different notation that you might see. So we already sort of did an example, 7 plus 11 and 7 times 11, and I didn't use this notation just because I didn't want to throw something else new in there. But notice here, if I have the plus with the subscript m, that's saying addition mod m. Same thing here, multiplication mod m. So just one more example using that proper notation. If I were to take 4 plus 5 mod 3, then again, I could turn them both into mod 3 first, or I could just say, and that's what this property says, just take 4 plus 5 to get 9, and then make that congruent to whatever that is mod 3. So mod 3, that would be 0 mod 3. And again, it would be 0 because 3 goes into 9 evenly. If I were taking 4 times 5, that would give me 20. Again, notice I'm using an equal sign because it's just regular math. But now if I'm turning it into mod, I'm saying that's congruent to. And then 3 goes into 20 with a remainder of 2. So it's 2 mod 3. So again, just another notation you might see with the mod 3 addition and multiplication. Coming up next, we're going to start to explore some integer representations. We're going to start with decimal expansions from binary, octal, and hexadecimal.